And so if there is anything specific that you had for Dan, Colin, or myself, if you want to know, if you have any questions about some of the technical details on, say, food production or energy, we can go into that a bit more. And there are quite a number of papers and references we can direct you to if you would like more technical information or resources to look into.
And I did hear
My
someone mention. Oh, go ahead.
Yep.
My thing is like micrometeorites or like dust storm issues that might
Yeah, and I'll
arise
bounce
with.
that over to Dan, who's done a lot more on the greenhouses that will be topping all of our colonies.
Sure. So, Corey, having that tessellated structure, when it kind of expands like a cubic spiral, and kind of the picture behind me, is it switching to mine or?
Yeah, here I can pass the hosting back to you.
Okay. I just don't know if I'm appearing on everyone's screen, so the background image is there.
Well, I see you and I see your background image, and I see the greenhouses over the like.
Oh, okay. Am I on the main screen or just the little one?
So
You're
that's
just a little one.
everyone can customize on their own Zoom. If you'd like to be the main screen, you should share your screen to take the whole screen.
Okay, no, just the background.
Yep.
So it still has you as the main here.
That's a setting that you have on your Zoom. Let me here. I can share that image though.
It says webcam, virtual background. It was going to Corey when he was speaking, but now that I'm speaking, it's not going.
Yeah, so that's a setting specific to your Zoom. It's called speaker mode, where you will be. So if you can pass the hosting back to me, I can do some photos while I can curate some photos while we do Q&A.
Sure. Okay. Sorry about that.
No problem.
Yeah, so micrometeorites, when you have that tessellated cubic spiral, you actually have a lot of potential redundancy there. So, okay, Stelly pulled this one up. That's good. So it's actually in. Sorry, Stelly, can you have it go to just the background and my video?
So no, that's not an option. You can. So I mean, you can change the background.
Can you have just the video of me be the main instead of? I think you're doing share screen.
So I'm currently sharing my screen, but if I stop sharing my screen, it's not going to make the video that you have the whole screen. You have to share your screen in order to take the whole screen, if you'd like to do that.
Or just the speaker mode. Okay. All right. I'll just share my screen because I think that will be easier.
All right.
Apologies for that.
No problem. That's one of my biggest issues is the micrometeorites and the dust storms. And
yeah, so that greenhouse that's hovering up above could have a lot of compartmentalization in there. You can see it kind of spirals out, and there's a lot of ability to individually kind of segment this off so that if a micrometeorite does come and hit, we can isolate it pretty rapidly with an airlock system. Also, the greenhouse, if you're growing higher plants, it has to be at a third atmospheric pressure, but actually the algae only needs to be above the triple point of water. Plants think that they're under water stress if they're less than a third regular standard atmospheric pressure, but algae just have to be. So you're talking about a pressure differential of like 0.01 psi for Mars. We just have to pressurize it a little bit so that it can be liquid water essentially. So all these blocks that potentially have just algae, a dilute solution of algae in them, say maybe a half meter thick, basically any micrometeorite coming in, there's actually 3 layers of plastic coming through that and a half meter of water. So that should take care of a certain size of particle. If there is a nearby meteor strike, I'm not sure, what the frequent size and velocity of those are, but that kind of offers one level. And then for a massive hit, kind of being in those linear foci. Let's see, do I have that one here? Let me jump through to that. Oh, yeah, being in these linear foci, especially starting at where they're only about 100 meters in width, is that's a very relatively small target, and it's kind of long and narrow with partitions across it as well. and then going to another one. So if there was a meteorite hit, if there was an asteroid hit, you would have kind of that built-in compartmentalization. With the dust, using compressed air to blow off the dust, maybe not brushes that would be abrasive, but using a simple kind of Roomba type of compressed air type of pneumatic dusting element might be good, and some of the dust will actually help mitigate UV radiation. So even if there is fine dust that can't be lifted off that greenhouse surface, that's okay, because there's plenty of sunlight for algae to grow at a very high rate, even with a light dust coating. And actually, it might help the UV mitigation. Originally, I thought about incorporating some of that dust for UV mitigation. I said, oh wait, it's just going to settle. A lot of the fines are going to settle right out on that surface anyways. So that might help with the longevity of the plastic. The mass of UV protectants is incredibly low. So even if we have to bring a few kilograms of UV protectant to incorporate into the plastic, like titanium oxide and such, it's a very low mass solution for UV mitigation. So those were a couple things, and then I think at the beginning you mentioned aerogel. For this to occur, you would definitely need an underlayment of aerogel, because Mars, the subsurface temperature of Mars is presumably very cold.
I heard you say aerogel, but you're breaking up.
Oh, so on the aerogel, you would need an aerogel underlayment to make this happen, and otherwise, it would freeze out. So aerogel, I think, is a good material for an underlayment with the Mars regolith contact surfaces, but probably not for the overhead material. First off, you don't really need it if you're suspending it. You kind of want it in the most air as possible, the least amount of regolith conduct for the least amount of heat loss. But also, aerogel looks to be a little bit hard to make in situ, and it has high molecular weight. So deep space radiation, GCRs, if they hit aerogel, you're actually going to get more secondary radiation off of aerogel versus a hydrocarbon plastic with water, because of the molecular weight that's used in aerogel.
And additionally to the fabrication side of things, so aerogel is one mechanism to insulate the ground. So a lot of our thermal losses are conductive thermal losses, and aerogel is one mechanism, but as Dan noted, it's very hard to produce, requiring supercritical CO2. So aircrete, so foamed concrete, is another mechanism that can be used, because you can use a deeper layer of that to get the conductivity characteristics that you need. And vacuum setting concretes are an active thing that will need to be developed for this, so it's within the scope of the project already.
And if we don't have any other questions, Stella, could you pull up do we have in our presentation, I don't have it up right now, or in our paper, the time frame to reach 1 million people? Do we have that table? Because that's an exciting one. People might want to see.
Yeah, I can pull that up.
I don't think we talked much about that. And my apologies for that. Sure.
Give me just a moment here. Okay, and so.
Sorry, I think my internet cut out.
Oh, it's no problem. So this time frame.
The daily thing.
Yeah, I think this is what you're talking about. You're currently the host, so you have to pass that back to me to share.
Oh. Okay.
I believe this is what we're looking for in terms. Sure. Yeah.
So yeah, I can talk a little bit about this too, because I should have included this in my presentation. I apologize. So at a rate of replication of every 3 years, basically you take that biomass from that initial greenhouse structure, and you can basically replicate that same amount of mass and volume every 3 years on Mars, converting that biomass to more plastic greenhouse material. 18 years is where we're looking at to get, the amount of acres to, wait, are those boxes missing? Where are we at? Oh yeah, that's 1 million people, right? 18 years, kilograms. Where's our population on here? Did we lose?
Is this the one you're looking for? Because I know that this is more population based, so there's not a combined table. I'm not sure which one you're referencing.
Okay. Let's head back up to that top table. Or, yeah, I guess it's in the text portion of it. But when you get to you know, acres of greenhouse up above 10 million, can you scroll down, I think, a little bit?
Yeah.
40, yeah. So at 45 years, we're at, oh, sorry, can you scroll up just a little bit more so we can see the top of the table? Does it? Yeah, there we go, perfect. So after 42 years, we kind of split the table up into two just so it didn't run too long. After initial amount of plastic, 200,000 kilograms, year one, by year 42, you're making, you know, 51,000 acres of greenhouse, which can essentially, with a tenth of an acre per person, I believe that goes up to, what's the math on that? Oh, there it is, 45. Okay, because the math didn't work out. Sorry, my toolbar is hiding year 45 below that, where it actually comes out to 1 million people. So with that 102,000 acres of greenhouse at year 45, that's where you hit the million person threshold from acres of greenhouse to support 1 million people. With a very relatively small, you know, you're starting at 3 acres of greenhouse at year one. So you're going from 3 acres of greenhouse at year one all the way to 102,000 acres of greenhouse, you know, in a slow and steady expanding rate, which I don't think there's any way to do that using photovoltaics or nuclear or what was the other? Oh, or like LEDs, basically, you know, growing food at that scale, as much as you could optimize a space with LEDs and, you know, and different planting architectures and stuff like that, there really doesn't, you know, you really need a huge amount of solar lit area to grow crops to support that many people. So yeah, just wanted to highlight that.
So Daniel, it's Mike. So one question I had was the point of diminishing returns. So on this, so if you have one system, at what point then is the cost benefit ratio then more costly than obviously the benefit, or the point of diminishing returns? And what
so the main constraint is the 1 to 3 kilowatts to make kilograms of plastic per hour. What's really nice is it's balanced well from a power standpoint between making the making of the biology is a nice slow steady rate. The plastic production is nice and slow and steady, and then the manufacturing, if we're doing 3D printing, is also very balanced. So it's kind of 3 very well balanced where there's not a lot of bottlenecks between them. The biggest bottleneck is the conversion rate from biomass to plastic. And also when you're going like from say year 42 from 51,000 acres of greenhouse to year 45, doubling that in just 3 years, who know, you know, hopefully we'll have, you know, cold fusion by that time. And, you know, the power required to do that conversion, you know, from an estimate based, you know, trying to calculate, you know, how much photovoltaics or nuclear, or maybe we have a more refined process that takes a lot less power. It's hard to, you know, the biggest part of the demand from a power standpoint is pushed towards the end of the colony development. So it's hard to estimate those at the far end.
I do just want to then reiterate 90% savings and the overall cycling and energy that can get dumped into other things. So those numbers right there don't in any way factor in the wetland components that are doing 90% of the cycling. So, and actually, Dan, I apologize. I never really thought about until this moment that we never factored in the wetlands. It could be way better than that. Because if I can get you that 90% of extra energy back from day one, Well, not day one. I mean, it's going to be all the robots land, and my guess is 5 to 10 years out before we're even trying to do some wetlands and really get those components. But then from there, that point after, then we'd have another modifier into the equation that would allow us to dump that energy back into something else. And so
one
we should
additional
probably
note
go back and take a
about
look at that.
One additional note about that, something else as well too, is that so this plastic that we're talking about, bioproduced plastic for the greenhouse, is not representative of all plastics that will be produced within the colony itself, nor all the bioproduction that we're going to use specifically even from an algal source to begin with. So this is part of a much larger infrastructure, and while this is highlighted as one of our rate limiting factors in terms of we need this greenhouse to fundamentally support the population that we're looking at, this is part of a larger system that's going to have very discrete efficiencies based on the production rates and usage of all those other things. We have a combined heat and power system, which is going to vary quite a bit seasonally. There's a lot that goes into that efficiency calculation.
Right, but is this one site or is this multiple sites?
Yeah, so like Stully had suggested, what was the number you said? The Fibonacci number for?
So 29, but 29 is the total number of settlements, but yeah, production can occur in different, in centralized areas and then be distributed.
I think with this model, we were talking about 10 starships landing at 10 different locations, or maybe it was 5 at 5 locations. So basically like picking different foci and landing these differences, actually paired landings at each foci, and then building in separate directions, kind of east and westbound. That way they do have kind of a nearby redundancy.
Right. So, but at what point is one site, one greenhouse site, at what point does it reach diminishing returns?
So what's the longevity of the greenhouse? The plastic lasts for 140 years. So the diminishing returns of that greenhouse will be beyond the scope, like with UV degradation. I mean, even with UV degradation, the useful life of this greenhouse will be a minimum of 20 years, very likely 40 years, and the plastic itself doesn't degrade for over 100 years. So the diminishing returns off that, again, the main bottleneck, I guess, is that biomass, the plastic conversion reactor, which is very low mass. Maybe I'm not understanding your question on diminishing returns.
Well, when the cost of running one site outweighs the benefit of that one particular site.
Basically, it's all driven by that biomass to plastic conversion factor. Right. Is, at what point do we need another biomass conversion reactor to keep expanding, and to keep up with that
specifically
biomass?
Within the industrial production chain for that for that plastic, it's going to be the pumping and the tank size and the tubing that's going to be our limit. So you can look at a series of tanks, but then pumping becomes your limit. You can look at larger pumps, but those become limited by the production of those pumps, which would be considered to be produced domestically at this point.
Okay.
And for the pumping, we didn't get into that detail, but we did look at using vertical axis wind turbines to do some of that pumping, because it is, the next step is how do you move the algae? How do you aerate the algae with CO2? As this system scales really rapidly. So there's a good paper from Denmark, I believe it is, that we cited in our paper that did wind tunnel or vacuum chamber wind testing, and we used those energetic levels to see what we could actually do with the wind power on Mars. So we do have maybe pneumatic is a central architecture to this. Instead of using electrical power, what can we just do with pneumatic power to support the base concepts in this design?
So another question I had in your design is the effect of gravity. I mean, Mars is at 0.38, 38% that of Earth. So how does this system become more optimized based upon lower gravity, or are you introducing other problems not foreseen that are affected by 38%?
The lower gravity makes say to pressurize the habitable area, say underneath the greenhouse, with Earth-based gravity, it would be 10 feet of water to create 1/3 atm atmospheric pressure. but on Mars, it's actually 30 feet. Is if you want to perfectly balance off the forces, you need 30 feet of water because of the reduced gravity there. Now, 30 feet of water over your head sounds terrifying and structurally impossible. But if you think of the reduced gravity, oh, okay, it's just think of it like 10 feet of water over your head. So that if all that stuff comes crashing down, it won't be quite as violent.
Right.
So that's the only gravitational factor that I've played into this. Absolutely, like the pipes and everything would need additional sloping, like the run to rise ratio for plumbing for Martians, for a Martian colony would be different than Earth. We didn't get to that level of detail though.
And that one's pretty easy. I was up at a site today where we had a pipe that was put in that was too small. 4-inch pipe. It's good enough for handling the load of the water going through the system, but when a little bit of material gets in there from one of the reactors, yeah, it can clog. Just basic maintenance. And having larger pipes is one of the easy ones. You know, just whatever that percentage. You know, so it's going to have to be 62% larger overall. And even, you know, would oval pipes be better than circular pipes? So the, you know, pretty kind of basic constraints, at least from my end. That's seemed to me like the easiest workaround. You know, don't you don't have to reinvent the wheel. Just we need bigger pipes, more material, more ferrocrete or you know, the Marscrete of some kind. I mean, obviously we need to do insulation like Stella had been talking about and Dan were talking about earlier. But those would be probably about the limit. But let me think more on it. And if you Mike, if you could come up with any other things, please, we'd love to get your thoughts.
Yeah, great, thanks.
All right, so that's actually a really great transition point. So unless there are any pressing questions here for a last one real quick, we're going to move over to the Mars Society more specifically. So any last questions about the solar punk colony?
Do you think that the EAU is watching you and stole your idea?
Hopefully.
Who is it?
The United Arab Emirates, their plan is to build in the canyons and to cover them with aerogels and water.
I just converted my PCT to a national phase for the United Arab Emirates, so they'll have a patent to stop them.
Oh, well, they came out with the drawings last year, and or the year before, and I was looking at them thinking, how brilliant! Cover a canyon, because my plans are to build a mile underground, a spherical city that is 50 stories high and 2 miles wide. So, and that covers the radiation and the pressurization and all that. But we need greenhouses on the surface because, yeah, we can't produce enough hydroponically underground.
And even if the initial settlements are, you know, underground, and then we have these sprawling greenhouse acres that are just food production, you know, and you know, okay, you're out in 1 or 2 hours. You don't have to worry about, you know, the radiation for that extended period of time. It's just, it's got to be greener. The space architecture's got to be greener.
No, it's got to. There has to be a green element to it. And what if something hits yours? We still have ours underground, and our there. So I think it's more about teamwork with all the different factors coming in. I like it. I love it.
So that's actually a great lead in again to a bit of information. So this webinar today was on this year's City-State Design Contest by the Mars Society, but we're going to actually be starting a series of webinars. So in 2 weeks, we're going to be doing a much more detailed version of run through of the self-organizing wetland bioreactors that Colin presented. So similar format, and you'll see the links going up for that in about a day. But join us again in 2 weeks for that. And in a month from today, we'll be going through a design that I pioneered from last year's colony, which is for 1,000 people. So if you want to see a bit earlier of this, what are some of the more critical systems that we'll have to start with, and what are some of the considerations given a much, much smaller population? We'll talk about that then. But beyond that, It's going to be up to the Mars Society to identify what we're talking about, and I'm going to pass it over to James to give you guys a bit more of a breakdown on that.